Picture an explosion so monumentally powerful that in mere seconds it releases more energy than our Sun will produce throughout its entire 4.6 billion year lifetime. Let that sink in for a moment. A single cosmic event that outshines billions of years of solar energy in the blink of an eye. This is just the beginning of what I'm about to share with you about one of the most extreme phenomena in our cosmos, the hypernova. Today, we're going to embark on an extraordinary journey through the mysteries of these cosmic titans. We'll uncover the fascinating secrets that set hypernovae apart from their more common cousins, the supernovae. You'll discover why these celestial explosions are incredibly rare, occurring only under the most exceptional circumstances in our universe. And perhaps most intriguingly, we'll explore how these massive eruptions fundamentally shape and transform the very fabric of our cosmos, leaving an indelible mark on the evolution of galaxies and the creation of elements essential for life itself. When we talk about hypernovae, we're venturing into the realm of the most energetic events ever witnessed in the universe since the Big Bang. These cosmic explosions are nature's ultimate demonstration of raw power, dwarfing virtually every other astronomical phenomenon we know of. They're so bright that if one occurred even in a nearby galaxy, it could potentially be visible from Earth in broad daylight. Before we dive deeper into this extraordinary phenomenon and unravel its mysteries together, I invite you to join our growing community of cosmic explorers here at Exploring the Universe. Hit that subscribe button and don't forget to turn on notifications by clicking the bell icon. This way, you won't miss any of our fascinating content about the wonders of astronomy, from the birth of stars to the dance of galaxies and everything in between. Let's dive deep into the fascinating world of hypernovae, nature's most spectacular stellar explosions. A hypernova represents the most extreme form of stellar death known to astronomy, an explosion that makes even the mighty supernova look modest in comparison. At its core, a hypernova is essentially a supernova on steroids, occurring when an exceptionally massive star, typically at least 30 times more massive than our Sun, reaches the end of its life in the most dramatic way possible. To truly understand what makes a hypernova special, let's first consider a regular supernova. In a typical supernova, a massive star explodes with enough force to briefly outshine its entire host galaxy, releasing energy equivalent to about 1044 joules. Now imagine cranking up that power by a factor of 10 or even 100. That's what we're dealing with in a hypernova. These cosmic behemoths can release energy upwards of 10 46 to 10 47 joules in just a few seconds. Let me put this mind-boggling amount of energy into perspective with some analogies that might help grasp its scale. Imagine all the energy our Sun will produce over its entire 10 billion year lifetime. A hypernova releases more energy than that in just a few seconds. If we tried to measure this in more earthly terms, a hypernova explosion releases more energy in a single second than humanity has produced in its entire history, multiplied by a factor of billions. But what truly sets a hypernova apart from its smaller cousin, the supernova, is not just its raw power. While both events mark the death of massive stars, a hypernova includes several unique characteristics. First, these explosions are highly asymmetric, often producing intense beams or jets of material that blast out from the poles of the dying star at speeds approaching that of light. These jets are so powerful they can be detected across billions of light years as gamma-ray bursts, the most energetic form of electromagnetic radiation in the universe. The sheer scale of a hypernova becomes even more impressive when we consider its reach. While a regular supernova might significantly affect a region of space spanning a few light years, a hypernova's influence can extend hundreds of light years, dramatically impacting its galactic neighborhood. The intense radiation and shock waves from these explosions can trigger the formation of new stars, seed the surrounding space with heavy elements, and even affect the magnetic fields of nearby stellar systems. To give you a final, striking comparison, if a regular supernova is like a cosmic nuclear bomb, then a hypernova is like a cosmic antimatter explosion. It operates on an entirely different level of physical extremes. The temperatures reached during a hypernova event can soar to several trillion degrees Celsius, creating conditions that haven't existed in the universe since moments after the Big Bang. These temperatures are so extreme that they can forge elements heavier than iron in quantities that regular supernovae simply cannot match, making hypernovae crucial players in the chemical evolution of our universe. The energy released in these events is so immense that if a hypernova occurred within several thousand light-years of Earth, it could potentially strip away our ozone layer and trigger mass extinctions. Fortunately for us, the nearest stars capable of producing hypernovae are safely beyond this distance, but this gives you an idea of just how powerful these cosmic explosions truly are. Let's delve into the fascinating prerequisites that must align for a hypernova to occur. First and foremost, we need an extraordinarily massive star, one that dwarfs our Sun in comparison. These stellar giants must have at least 30 times the mass of our Sun, though some can be much larger, reaching up to 100 solar masses or more. Such massive stars are incredibly rare in our universe, which partly explains why hypernovae are such exceptional events. The second crucial condition is rapid rotation. The star must be spinning at an astounding rate, often hundreds of times faster than our Sun. This rapid rotation is essential because it helps create the necessary conditions for the formation of powerful jets during the explosion. When such a massive star spins rapidly, it generates intense centrifugal forces that play a crucial role in shaping the eventual explosion's asymmetric nature. The chemical composition of the progenitor star also plays a vital role. These stars must have relatively low metallicity, which in astronomical terms means they contain fewer heavy elements than typical stars. This specific chemical makeup is crucial because stars with higher metallicity tend to lose too much mass through stellar winds during their lives, making them unsuitable for hypernova events. The lower metallicity helps the star retain enough mass to achieve the catastrophic collapse needed for a hypernova. Another critical factor is the presence of an intense magnetic field. As the star approaches its final moments, its core must generate and maintain an extraordinarily powerful magnetic field. These magnetic fields, which can be billions of times stronger than Earth's magnetic field, are instrumental in directing and focusing the energy of the explosion into the characteristic jets that define a hypernova. The magnetic fields act like cosmic railway tracks, guiding the expelled material along specific paths as the star explodes. These conditions must not only exist independently, but must also work in perfect concert. The combination of extreme mass, rapid rotation, specific chemical composition, and intense magnetic fields creates a cosmic pressure cooker that, when finally unleashed, results in one of the most energetic events in our universe. This precise orchestration of conditions explains why hypernovae are so rare and why they continue to captivate astronomers worldwide. When all these conditions align, the stage is set for a cosmic display of unimaginable power. The massive star's core, spinning rapidly and confined by powerful magnetic fields, finally reaches the point of no return. What follows is not just a simple explosion, but a carefully choreographed cosmic ballet of matter, energy, and magnetic forces that results in the most powerful explosions known to science since the Big Bang itself. The process begins with the exhaustion of nuclear fuel in the massive star's core. Throughout its life, the star has been maintaining a delicate balance between gravity pulling inward and nuclear fusion pushing outward. As the star runs out of lighter elements to fuse into heavier ones, it enters a frantic phase where it burns through its remaining fuel at an astronomical rate. This is like a cosmic version of a car engine running on its last drops of fuel, but on an unimaginably larger scale. When the core finally depletes its nuclear fuel entirely, what follows is perhaps the most dramatic moment in stellar evolution: the core collapse. Without the outward pressure from nuclear fusion to counteract gravity, the star's immense mass causes its core to collapse catastrophically. This collapse happens at mind-boggling speeds. In less than a second, the core shrinks from roughly the size of Earth to a sphere just a few miles across. The temperatures and pressures during this collapse are so extreme that they surpass anything we can recreate in laboratories on Earth. But unlike in a regular supernova, where the collapse might result in a neutron star, the sheer mass involved in a hypernova leads to something far more extreme: the formation of a black hole. The core becomes so compressed that not even light can escape its gravitational pull. This newborn black hole, spinning at incredible speeds due to the conservation of angular momentum, becomes the engine that powers what happens next. This is where the most spectacular part of the hypernova occurs: the formation of relativistic jets. As the remaining stellar material falls toward the newly formed black hole, it doesn't just drop straight in. Instead, the combination of the black hole's intense rotation and powerful magnetic fields channels some of this infalling material into two narrow beams that blast outward from the poles at speeds approaching that of light itself. These relativistic jets are so powerful that they can drill through the outer layers of the dying star like cosmic blowtorches. The jets carry an almost unimaginable amount of energy, more than our sun will produce in its entire lifetime. As they punch through the star's outer layers, they create shock waves that help blow the star apart in an asymmetric explosion. The jets also produce intense bursts of gamma rays, which is why hypernovae are often associated with the most powerful gamma-ray bursts we observe in the universe. The material in these jets is not just moving fast, it's moving at relativistic speeds, meaning close enough to the speed of light that Einstein's special relativity comes into play. This creates fascinating effects where time itself behaves differently within the jets compared to their surroundings. The temperatures within these jets can reach several trillion degrees Celsius, creating conditions that haven't existed since moments after the Big Bang. As this entire process unfolds, the hypernova releases an amount of energy that's almost impossible to comprehend. In just a few seconds, it outshines its entire host galaxy, spraying newly forged heavy elements across vast distances of space. The jets can extend for thousands of light years, influencing regions of space far beyond the original star's neighborhood. This extraordinary chain of events, from fuel exhaustion to core collapse, from black hole formation to relativistic jets, represents nature operating at its absolute extremes. It's a process that not only showcases the raw power of cosmic forces, but also plays a crucial role in seeding the universe with the heavy elements necessary for the formation of future stars, planets, and potentially life itself. When we talk about gamma rays associated with hypernovae, we're dealing with the most energetic form of electromagnetic radiation known to science. These gamma-ray bursts are so intense that they can be detected even from billions of light-years away. To put this in perspective, imagine being able to see a firefly on the moon. That's roughly equivalent to our ability to detect these bursts from the other side of the observable universe. These gamma-ray bursts are like cosmic lighthouses, briefly becoming the brightest objects in the universe, outshining everything else combined. The duration of a hypernova event presents a fascinating contrast between brevity and long-lasting impact. The initial explosion and gamma-ray burst are incredibly brief, typically lasting anywhere from a few seconds to a few minutes. However, what's particularly interesting is that we can observe the afterglow of these events for weeks or even months afterward. This afterglow, visible across multiple wavelengths of light, helps astronomers study the explosion's effects on its surroundings. It's rather mind-bending to think that an event lasting mere seconds can have consequences that persist for millions of years in the surrounding space. When it comes to frequency, hypernovae are extremely rare events. Astronomers estimate that in a typical galaxy like our Milky Way, a hypernova might occur only once every several 100,000 years. This rarity is due to the very specific conditions required for such an event. To put this in cosmic perspective, while a regular supernova occurs somewhere in the observable universe about once every second, hypernovae are hundreds of times rarer. This makes each observation particularly valuable to our understanding of these cosmic phenomena. Perhaps one of the most intriguing aspects for us earthbound observers is the concept of safe distance from a hypernova. The destructive potential of these events is staggering. If a hypernova were to occur within about 1,000 light-years of Earth, the resulting radiation could potentially strip away our ozone layer, leading to mass extinctions. Fortunately for us, the nearest stars capable of going hypernova are safely beyond this distance. The closest potential hypernova progenitor stars are several thousand light-years away, in the Eta Carinae system. Here's an interesting tidbit that often surprises people. The effects of a hypernova aren't limited to its immediate cosmic neighborhood. The jets from these explosions can travel through space for thousands of light-years, affecting regions far beyond their origin point. These jets can trigger the formation of new stars, create massive bubbles in the interstellar medium, and even influence the magnetic fields of entire galaxies. Another fascinating aspect is the role of hypernovae in the creation of heavy elements. These explosions are so powerful that they're among the few cosmic events capable of creating some of the heaviest elements in the periodic table. Elements like gold, platinum, and uranium that we find on Earth today may well have been forged in ancient hypernova explosions billions of years ago. In fact, it's possible that some of the atoms in your body were once part of a hypernova explosion. The detection of hypernovae has also led to some remarkable discoveries in modern astronomy. For instance, these events have helped confirm several predictions of Einstein's theory of relativity, as the extreme conditions during a hypernova provide a natural laboratory for testing physics at its limits. The way space and time behave around these events continues to challenge our understanding of the universe. One particularly mysterious aspect is the connection between hypernovae and long-duration gamma-ray bursts. While we now know that some hypernovae produce these gamma-ray bursts, we're still trying to understand why some do and others don't. This ongoing mystery keeps astronomers worldwide actively searching for answers, making hypernovae a frontier of modern astrophysical research. The timing of hypernova detection also presents an interesting challenge for astronomers. Because these events are so rare and happen without warning, catching one in the act requires a global network of telescopes working in concert, ready to swivel toward any potential explosion at a moment's notice. This has led to the development of sophisticated alert systems and international collaboration networks among astronomers, highlighting how these cosmic events drive technological and collaborative innovation in science. The discovery of GRB 080319b, famously known as the Naked Eye GRB, marked a watershed moment in our understanding of hypernovae and their associated gamma-ray bursts. Detected on March 19, 2008, this event was so incredibly bright that it was briefly visible to the naked eye from Earth, despite occurring 7.5 billion light-years away. To put this in perspective, imagine being able to see a firefly on the moon. Now imagine that firefly was floating somewhere beyond the edges of our galaxy. This event reached a peak magnitude of 5.8 on the astronomical brightness scale, making it the most luminous object ever observed by human eyes. For a brief 40 seconds, anyone looking at the right spot in the constellation Boötes could have seen light from an explosion that occurred when our planet was less than half its current age. SN 2006 Gi represents another groundbreaking discovery that forced astronomers to rethink their theories about stellar explosions. This extraordinary supernova, which some scientists classify as a hypernova due to its extreme characteristics, was observed in 2006 and remained bright for an unusually long time, nearly 100 days. What made SN 2006 GY particularly fascinating was its sheer size and energy output. The progenitor star is believed to have been a stellar giant with a mass around 150 times that of our Sun, making it one of the most massive stars ever observed to explode. The event released about 100 times more energy than a typical supernova, challenging our understanding of how massive stars die. Current research in the field of hypernovae is advancing at an exciting pace, with several key areas under intense investigation. One major focus is understanding the connection between hypernovae and fast radio bursts, FRBs. Scientists are exploring whether some FRBs might be associated with the aftermath of hypernova explosions, particularly in cases where the bursts repeat. This research could provide new insights into the long-term evolution of hypernova remnants. Another fascinating area of ongoing research involves the role of hypernovae in the production of heavy elements. Recent studies using advanced spectroscopic techniques have revealed that these explosions may be even more important than previously thought in creating elements heavier than iron. Scientists are particularly interested in understanding how hypernovae contribute to the universe's supply of gold, platinum, and other precious metals. Researchers are also making significant progress in understanding the precise mechanics of jet formation during hypernova explosions. Using sophisticated computer simulations that incorporate both general relativity and magnetohydrodynamics, scientists are beginning to unravel how these powerful jets form and propagate through space. These simulations are helping us understand why some hypernovae produce gamma-ray bursts while others don't. The hunt for potential hypernova progenitors has intensified with the advancement of observational technology. Scientists are closely monitoring several massive stars in our galaxy that could potentially become hypernovae in the astronomical near future. One such candidate is Eta Carinae, a massive binary star system about 7,500 light-years away. Advanced observations of this system and others like it are helping astronomers understand the conditions that lead to these extreme explosions. Perhaps one of the most exciting developments in recent years has been the integration of gravitational wave detection into hypernova research. Scientists are now working to correlate gamma-ray burst observations with gravitational wave signals, hoping to catch a hypernova in the act of forming a black hole. This multi-messenger approach to astronomy is opening new windows into understanding these cosmic explosions. The advent of automated sky surveys and rapid response telescope networks has revolutionized how we study these events. Projects like the Zwicky Transient Facility and the upcoming Vera C. Rubin Observatory are expected to dramatically increase our detection rate of hypernovae and related phenomena, potentially leading to the discovery of new subclasses or variations of these extraordinary explosions. Recent studies have also begun to examine the role of binary star systems in hypernova production. There's growing evidence that some hypernovae might result from the interaction or merger of two massive stars, adding another layer of complexity to our understanding of these events. This research direction could help explain some of the more unusual characteristics observed in certain hypernova explosions. These ongoing investigations and recent discoveries continue to demonstrate that hypernovae are even more complex and fascinating than we initially thought. Each new observation seems to raise as many questions as it answers, ensuring that this field remains at the forefront of astronomical research. The role of hypernovae in shaping our universe is nothing short of extraordinary. These cosmic explosions serve as fundamental architects of universal evolution, influencing everything from the chemical composition of galaxies to the birth of new stellar generations. Let's explore how these magnificent explosions have been crucial in creating the universe as we know it today. First, let's consider the production of heavy elements, a process that makes hypernovae truly special. During these explosions, temperatures and pressures reach such extreme levels that they create perfect conditions for nucleosynthesis, the creation of heavy elements. In mere seconds, a single hypernova can forge more gold, platinum, uranium, and other heavy elements than thousands of regular stars could produce in their entire lifetimes. This process, known as R-process nucleosynthesis, occurs so rapidly that atomic nuclei capture neutrons faster than they can decay, allowing the creation of the heaviest elements in the periodic table. Without hypernovae, many of the elements we rely on today simply wouldn't exist in their current abundances throughout the universe. The influence of hypernovae on star formation is equally fascinating. When these massive explosions occur, they create enormous shock waves that propagate through space, compressing nearby clouds of gas and dust. This compression can trigger the collapse of these cosmic clouds, leading to the birth of new stars. It's a beautiful cosmic cycle, one generation of stars ending in spectacular hypernovae, catalyzing the birth of the next generation. These shockwaves can travel hundreds of light years, affecting vast regions of space and potentially triggering the formation of entire stellar clusters. The energy and material ejected from hypernovae also enrich these star-forming regions with heavy elements, ensuring that each new generation of stars and their potential planetary systems are more chemically diverse than the last. In terms of galactic evolution, hypernovae play a pivotal role that extends far beyond their immediate vicinity. These explosions contribute significantly to what astronomers call galactic feedback, the process by which stellar events influence the broader galactic environment. The tremendous energy released by hypernovae helps regulate the gas dynamics within galaxies, preventing excessive star formation in some regions while promoting it in others. This regulatory effect is crucial for maintaining the delicate balance that determines a galaxy's structure and evolution. The impact of hypernovae on galactic magnetic fields is particularly intriguing. The powerful jets and expanding shells of material from these explosions can amplify and reshape magnetic fields on galactic scales. These modified magnetic fields, in turn, influence future star formation and the movement of cosmic rays throughout the galaxy. It's a complex interplay that helps determine the overall character and evolution of entire galactic systems. Moreover, hypernovae contribute significantly to the galactic fountain effect, where hot gas is propelled high above the galactic plane, only to cool and rain back down. This circulation of material is crucial for distributing heavy elements throughout the galaxy and maintaining the galactic ecosystem. The extreme temperatures and energies involved in hypernovae make them particularly effective at driving this galactic circulation, ensuring that the chemical enrichment of the galaxy is thoroughly mixed and distributed. The long-term effects of hypernovae on galaxy evolution are still being discovered. Recent studies suggest that these explosions may play a crucial role in regulating the size and mass of galaxies, particularly in the early universe. The enormous energy they release can expel significant amounts of gas from smaller galaxies, potentially explaining why we observe fewer very massive galaxies than cosmic models would predict. In essence, hypernovae serve as cosmic factories, recycling centers, and architects all at once. They forge new elements, scatter them across vast distances, trigger the birth of new stars, and help shape the very structure of galaxies. Their influence extends across billions of light years and billions of years, making them indispensable players in the ongoing story of our universe's evolution. Understanding these magnificent explosions isn't just about satisfying scientific curiosity. It's about understanding our own cosmic origins and the processes that made our existence possible. The detection and observation of hypernovae represent one of the most sophisticated collaborative efforts in modern astronomy, requiring a complex network of instruments and international cooperation that spans our entire planet and extends into space. Let's explore how astronomers manage to capture and study these rare and spectacular cosmic events. Space telescopes play a crucial role in hypernova detection and observation. The Hubble Space Telescope has been particularly instrumental in studying the aftermath of these cosmic explosions, capturing detailed images of their evolution over time. Its ability to observe in multiple wavelengths, from ultraviolet to near-infrared, provides astronomers with crucial data about the composition and behavior of hypernova explosions. The James Webb Space Telescope, with its unprecedented infrared capabilities, now allows us to peer even deeper into these events, revealing details about their chemical composition and the way they interact with their surrounding environment that were previously invisible to us. The Swift Observatory, launched in 2004, has revolutionized our understanding of hypernovae and their associated gamma-ray bursts. This remarkable spacecraft can detect a gamma-ray burst and automatically swivel to point its X-ray and ultraviolet optical telescopes at the event within seconds. This rapid response capability has provided astronomers with crucial early data about these explosions that would have been impossible to capture otherwise. Swift's ability to quickly alert ground-based telescopes has created a sophisticated early warning system for astronomers worldwide. The detection of gamma rays from hypernovae requires specialized equipment both in space and on Earth. The Fermi Gamma Ray Space Telescope has been instrumental in this regard, providing continuous monitoring of the entire sky for gamma-ray bursts. Its Large Area Telescope, ELAT, and Gamma Ray Burst Monitor, GBM, work in tandem to detect and analyze these high-energy events. When Fermi detects a burst, it immediately sends the coordinates to Earth, triggering a cascade of observations from other instruments. On the ground, facilities like the High-Energy Stereoscopic System, HESS, in Namibia, and the Very Energetic Radiation Imaging Telescope Array System, VERITAS, in Arizona, can detect the highest energy gamma rays from these events. These ground-based telescopes use the Earth's atmosphere as part of their detection system, observing the cascade of particles produced when high-energy gamma rays collide with air molecules. This technique, known as atmospheric Cherenkov detection, has opened new windows into understanding the most energetic aspects of hypernovae. The international collaboration required to study hypernovae is truly remarkable. When a potential hypernova is detected, astronomers worldwide spring into action in a carefully choreographed response. The Gamma Ray Coordinates Network, GCN, serves as the central nervous system of this collaboration, rapidly distributing alerts and coordinates to observatories around the globe. Within seconds of a detection, automated systems begin redirecting telescopes, while astronomers across different time zones coordinate their efforts to ensure continuous observation of the event. This global collaboration extends to data sharing and analysis. The International Astronomical Union helps coordinate these efforts, ensuring that observations from different facilities can be combined effectively. Major observatories like the European Southern Observatory in Chile, the Keck Observatory in Hawaii, and the Very Large Array in New Mexico often work in concert, each contributing unique observations that help build a complete picture of these cosmic events. The advent of gravitational wave astronomy has added another fascinating dimension to hypernova detection: the laser interferometer. Gravitational Wave Observatory and its European counterpart Virgo can detect the gravitational waves produced when massive stars collapse. When these detections coincide with observations from traditional telescopes, astronomers can gain unprecedented insights into the physics of these explosions. This multi-messenger astronomy approach, combining observations of light, gravitational waves, and potentially neutrinos, represents the cutting edge of hypernova research. Advanced computing systems play a crucial role in processing the massive amounts of data generated by these observations. Supercomputers analyze the spectral signatures of hypernovae, helping astronomers determine their chemical composition and physical properties. Machine learning algorithms are increasingly being employed to sift through astronomical data, helping to identify potential hypernova candidates and unusual features that might otherwise be missed. The future of hypernova detection looks even more promising. New facilities like the Vera C. Rubin Observatory, with its unprecedented survey capabilities, will scan the entire visible sky every few nights, potentially discovering many more hypernovae and related phenomena. The continued development of space-based gravitational wave detectors and improved gamma-ray telescopes promises to further enhance our ability to study these cosmic explosions. The study of hypernovae through this sophisticated detection network has transformed our understanding of these events from rare, mysterious occurrences to well-documented cosmic phenomena. While each new observation continues to surprise us with unexpected details, our growing ability to detect and study these events in real time has revolutionized our understanding of the most energetic explosions in the universe since the Big Bang itself. When we contemplate a hypernova, we must transcend our conventional understanding of what constitutes an explosion. This is not merely a violent end to a stellar life. It is nothing less than a cosmic alchemist's workshop operating on an unimaginable scale, a celestial forge that fundamentally rewrites the chemical destiny of entire galactic regions. In those brief, blindingly brilliant moments when a hypernova erupts, we witness the universe's most sophisticated element factory in action. Within the heart of this cosmic inferno, where temperatures soar to levels unseen since the first moments after the Big Bang, atomic nuclei dance and combine in ways impossible anywhere else in the modern universe. Each explosion is a masterclass in nuclear physics, creating in seconds what would take billions of years to produce through any other natural process. Consider this. Every atom of gold in your wedding ring, every trace of silver in your electronics, every particle of platinum in a catalytic converter. These precious metals were likely born in the heart of such cosmic cataclysms. The heaviest elements in the periodic table tell a story of their violent birth in these extraordinary explosions, where neutron-rich environments create the perfect conditions for rapid neutron capture, the only known natural process capable of forging many of our heaviest elements. But a hypernova's influence extends far beyond its role as a cosmic factory. As its shock waves propagate through space, they become cosmic sculptors, compressing vast clouds of gas and dust, triggering the birth of new stars and planetary systems. These shockwaves carry within them the newly forged elements, seeding the surrounding space with the building blocks necessary for the next generation of cosmic structures. It's a grand cosmic cycle of death and rebirth, where the end of one massive star provides the essential ingredients for thousands of new stellar systems. What makes this process truly remarkable is its direct connection to our own existence. The calcium in our bones, the iron in our blood, the phosphorus in our DNA, while not all created in hypernovae, their relative abundances in our corner of the cosmos have been significantly influenced by these spectacular explosions. Every time we look in a mirror, we are quite literally observing the products of ancient stellar explosions that have been incorporated into living matter. The hypernova represents nature's most extreme demonstration of the principle that destruction and creation are two sides of the same cosmic coin. In its fury, it destroys a massive star, Yet in doing so, it enriches the cosmic web with the elements necessary for complexity, for chemistry, for life itself. It is both an ending and a beginning, a death that enables countless new possibilities for future astronomical generations. As this cosmic drama unfolds across the vast theaters of space, it reminds us that we are witnessing something far more profound than a mere explosion. We are observing one of the universe's primary mechanisms for increasing complexity, for ensuring that each generation of stars and planets has more chemical possibilities than the last. Through hypernovae, the cosmos transforms simple hydrogen and helium into the rich variety of elements necessary for planets like Earth to form, for chemistry to diversify, and ultimately, for life to emerge. In the end, a hypernova stands as a testament to the universe's remarkable capacity for transformation. It demonstrates how the most violent events in cosmos paradoxically create the conditions necessary for the most delicate and complex structures to form. From destruction comes creation, from chaos emerges order, and from the death of a single star comes the potential for countless new worlds. This is the true legacy of a hypernova, not just as an explosion, but as a fundamental force in the ongoing evolution and enrichment of our universe. When we look into a mirror, we're actually gazing at star stuff, matter that was forged in the hearts of ancient stars and violent cosmic explosions. The human connection to hypernovae runs deeper than mere scientific curiosity. It's literally in our bones, our blood, and our DNA. Let's explore this profound connection between these cosmic explosions and our very existence. The calcium that strengthens our bones and teeth has a fascinating origin story that leads back to stellar explosions. While regular supernovae produce significant amounts of calcium, hypernovae are especially efficient at creating and distributing this essential element throughout the cosmos. Every time you bite, smile, or move, you're utilizing atoms that were once part of these cosmic explosions. Our blood tells an equally compelling story. The iron that makes our blood red and carries oxygen throughout our bodies was created in massive stars and scattered across space through events like hypernovae. When we talk about having star stuff flowing through our veins, we're being literally accurate. The iron in our hemoglobin was likely forged in ancient stellar explosions billions of years before our solar system formed. Even more remarkably, many of the trace elements crucial for human life bear the signature of hypernova explosions. The selenium in our proteins, the zinc that supports our immune system, and the copper that helps form our connective tissues. All these elements exist in their current abundances, partly due to the cosmic distribution network of hypernovae. Each breath we take, each heartbeat, each thought firing across our neural networks involves atoms that were once part of these magnificent cosmic events. The gold in our jewelry and the silver in our electronics tell similar tales. These precious metals are among the heaviest naturally occurring elements, and their creation requires the extreme conditions found only in the most powerful stellar explosions. When you wear a gold ring or use a silver-containing device, you're carrying a small piece of a hypernova's legacy. Understanding this connection helps us grasp our place in the cosmic story. We are not merely observers of the universe, we are literally made from it. The violent deaths of massive stars through hypernovae have played a crucial role in creating the conditions necessary for complex life to emerge. Every person on Earth is, in a very real sense, a collection of atoms that have traveled through space and time, shaped by cosmic forces, including these powerful explosions. This realization transforms how we view our relationship with the cosmos. We're not separate from these distant cosmic events. We're their direct descendants. The same processes that create the spectacular light shows astronomers observe in distant galaxies also created the building blocks of our bodies, our planet, and everything we interact with daily. Moreover, this connection to hypernovae helps us understand our cosmic heritage. The fact that these rare, violent events were necessary to create many of the elements we depend on demonstrates the remarkable sequence of events required for our existence. It's a humbling reminder that we are part of a vast cosmic cycle, where the death of massive stars creates the conditions necessary for life as we know it. The next time you look up at the night sky, remember that you're not just observing distant cosmic events. You're looking at the kinds of processes that created the very atoms that make up your body. We are, quite literally, the universe observing itself, made possible by the incredible astronomical phenomena like hypernovae that have enriched our cosmos with the elements necessary for life. This profound connection between hypernovae and human existence reminds us that astronomy isn't just about studying distant objects and events. It's about understanding our own origins and the incredible sequence of cosmic events that made our existence possible. We are living proof that the universe, through processes like hypernovae, has found a way to transform simple elements into conscious beings capable of contemplating their own cosmic origins. As we conclude our journey through the extraordinary phenomenon of hypernovae, let's reflect on the profound insights we've uncovered about these cosmic titans. These stellar explosions, representing nature at its most extreme, have emerged as fundamental architects of our universe, shaping not just the cosmic landscape, but our very existence. Throughout our exploration, we've witnessed how hypernovae distinguish themselves from regular supernovae through their unprecedented power and reach. These aren't merely bigger explosions. They're fundamentally different events that operate at the very limits of what's possible in our universe. In mere seconds, they release more energy than our sun will produce in its entire lifetime, creating conditions that haven't existed since moments after the Big Bang. We've learned that these cosmic events require a precise orchestration of conditions: exceptionally massive stars, rapid rotation, specific chemical compositions, and intense magnetic fields. This remarkable combination of requirements explains their rarity and makes each observation particularly valuable to our understanding of the cosmos. The impact of hypernovae extends far beyond their immediate vicinity. They serve as cosmic forges, creating many of the heaviest elements in our periodic table. They act as galactic sculptors, triggering the formation of new stars and shaping the structure of entire galaxies. Their influence reaches across billions of light years and continues to affect cosmic evolution billions of years after the explosion itself. Perhaps most remarkably, we've discovered our intimate connection to these distant cosmic events. The atoms in our bodies, the calcium in our bones, the iron in our blood, and many of the trace elements essential for life bear witness to ancient hypernovae that erupted long before our solar system formed. We are, in a very real sense, children of these cosmic explosions. Modern astronomy's ability to detect and study these events represents one of humanity's greatest scientific achievements. Through an intricate network of ground-based and space-based observatories, we can now observe these cosmic titans in unprecedented detail, unlocking new mysteries about the universe and our place within it. As we look to the future, hypernovae continue to challenge our understanding and push the boundaries of our knowledge. Each new observation brings fresh insights and raises new questions, driving forward our quest to understand the cosmos. They remind us that we are part of something vastly larger than ourselves, a universal story written in starlight and cosmic explosions. And now, if you've found yourself captivated by this cosmic journey through one of the universe's most extraordinary phenomena, I encourage you to join our growing community of cosmic explorers at Exploring the Universe. By subscribing to our channel and activating notifications, you'll ensure you never miss our latest adventures into the cosmos. Each like and share helps spread the wonder of astronomy to others who share our fascination with the universe's greatest mysteries. Remember to click that subscribe button, turn on notifications by hitting the bell icon, and show your support with a like. Share this video with friends and family who share your interest in astronomy. Together, we can build a community united by our curiosity about the cosmos. Join us at Exploring the Universe as we continue to unravel the mysteries of our universe, one celestial wonder at a time. The cosmos is vast and full of wonders, and we're just getting started on our journey of discovery. Until our next cosmic adventure, keep looking up and wondering about the magnificent universe we call home.